We shall start with figure 2.1, time, fuel, and distance to climb. And in our example, we shall be making the following assumptions: that the power will be full throttle at 2,500 RPM. Fuel density is 6 pounds per gallon. Mixture will be full rich, and the cowl flaps will be as required, and cowl flaps serve to cool the engine. The other assumptions that we will use in this example of calculating time, fuel, and distance to climb would be our temperatures, pressure, altitude, as well as mass. And we'll start by looking at the mass. The initial mass of this particular aircraft in this example will be 3,650 pounds. And what that means is that at the start of the takeoff, that is how much the aircraft will weigh. The OAT at takeoff, or the outside air temperature at takeoff, will be 15 degrees Celsius. The airport pressure altitude will make it simple for this first example, and we'll assume that the airport is at sea level. So we're taking off from sea level, and we're going to climb to a place where the outside air temperature is going to be negative 12 degrees, and our cruising pressure altitude will be 10,000 feet. So we need to solve for these three things: time to climb, fuel to climb, and the distance to climb. Distance to climb, as a reminder, these charts all do not take into account wind, so the distance to climb will be in nautical air miles, that is, still air distance. So we're going to look at a few things first. This example, we keep it simple by taking off at sea level, so you only need to plot one line. And I'll explain why you might have to do more than one plot to get this data later on in the other examples. But for now, we're just going to assume that we're taking off from an airport at sea level and the temperature is 15 degrees Celsius. This seldom ever happens, but we're making that assumptions to keep the example simple. Let me bring you around the chart. We will enter the chart from this side, which says outside air temperature, where we will match the outside air temperatures to the pressure altitudes. And then we will move across the chart to the masses reference lines, and then we will come down to where we will extract the information that we're looking for, which is time to climb in minutes, fuel to climb in gallons, and distance to climb in nautical miles. Let's zoom into the start. Because we're taking off at sea level, we do not need to account for the sea level airport. We will be taking off from this line where the datum is going to be 0, and we will straight away look for what the temperature is at our chosen cruise pressure altitude. And the temperature that we have decided, and we would get this information from a weather report, would be that at 10,000 feet the outside air temperature will be minus 12 degrees. So this is the outside air temperature scale, and on this side of 0 is positive, on this side of 0 is negative, and we have said that our temperature will be negative 12. So this is negative 10, negative 12 will be 1 square to the left, because that's 2, 4, 6, 8, minus 20. So what we're going to do right now is we're going to plot a line from negative 12 all the way up to meet our altitude at 10,000 feet. You can see that I've now plotted the line of negative 12 degrees to meet my altitude at 10,000 feet. We're now going to go across the chart in this direction to meet the initial mass lines. And we want to make sure that we meet the mass line for 3,650 pounds, which is our initial climb mass. So we've gone from minus 12 degrees Celsius climb to 10,000 feet and we move across to the initial climb mass of 3,650 feet. And now we simply extend the line down to meet our time, fuel, and distance to climb scales. And we arrive at a time to climb of 10, 11, 12, 13 minutes. And we would arrive with a fuel figure of 4.7 gallons and a distance to climb of 27 minutes. 13 minutes, 4.6 gallons, and 27 nautical miles. And we've drawn 3 lines and extracted the information from these 3 scales, and it's as simple as that.